Hello everyone and welcome to this new Wii episode for the STM32 tutorial, and today we are going to explore the interrupt for the ADC. So we have been looking at the ADC, how to create a basic function, how to read the data, how to use it in a way, but this is the first time when we go through the interrupt or the IRQs. So within this episode we will build the whole thing from scratch. And also, as you can see here, we will be having a time analysis and understanding how effective using IRQ against a normal ADC function. So if you are interested to learn and understand how all this works, this is the right episode for you. Hope you enjoy, and let's start. As usual, we are starting with the chapters of our tutorial. So first of all, we will take a look on the circuit. Nothing has changed against the last one, but we will explain a little bit for which pin we are going to allow or to assign the IRQ and which pin we are going to use for normal ADC activity. Then we will initiate the ADC IRQ function. So we will see how you can initiate the ADC using the IRQ or having the interrupt. After that, we need to assign the pin to the ADC, because the approach here in this solution is more to work on the ADC and how you will set up the ADC for to have the interrupt, and then you can change the pin. So this is a little bit different approach against the one where you select the pin and use the pin than this one. This one is more working at the ADC level. After that, we need to use the handler. So as we have seen for the GPIO, it's always important to understand how we use the handler, and within the handler, how we will manage when we get a signal. Then we would be reading the data function. So after we assign the whole thing and as we work on the ADC level, we will be just reading the data from the ADC, because as we have seen, the ADC have one data register that will depend on the selected channel. So we can get just the data of the ADC knowing that we are working on a certain channel. Then we will have a live test, and this live test will be looking at a time analysis and also comparing with a normal ADC. And of course, we need to know how to stop the IRQ or the interrupt. Finally, warning with IRQ, what a weird English I'm using today, but this is the risk when you use an IRQ and the things that you should be worried about. Good. And if this is the first time we are using the for you to join this video, the board is the STM32 Endeavour F4VE. This is the Chinese-made board that I really love, and we will see later on in future video when we will use the SPI and the NRF, how fascinating and easy hand-on to integrate the NRF. And the microcontroller is the STM32F407 VET6. And very important to note also that, let me hide the video quickly, that I'm connecting that board with a GTag. So if you download the code that is available on the GitHub and you don't have a GTag, you need to go to the debug and change this one to the ST-Link. So don't forget that. I'm doing this especially so you can see a diversity of way that you can use to program your ARM microcontroller. So let's get back again here and let's jump to the next chapter. So let's go and let's have the circuit review. So first of all, we do have a sliding potentiometer, same as the previous tutorials. And also we will have a rotary potentiometer. We will have the PA1, so the port A, pin number 1, that will be an input for the slide potentiometer. So the the analog input will be connected with this sliding potentiometer, and the PA4 will be connected with ADC2. So PA4 later on will have the IRQ function and will be connected with the rotary potentiometer. So the first one, the PA1, will not be connected, will be connected with ADC1, and that will be a normal way of using the microcontroller, where the PA4 will be using the IRQ or the interrupt. Then for our signal analysis, we will use PA0 as an output for the logic analyzer, and to read how long it takes to read the data using PA1 or a normal ADC way. So just keep waiting and the result is ready. Where in PA5, that will be the output, so the pin PA5 for the logic analyzer to read how long it takes for PA4. So we will see the efficiency of using the interrupt against using the normal way. Good, so let's go for the next part of the chapter, which will be initiate the ADC IRQ function. So let's start by hiding this, and so I already put somehow the high level of this one. So we will take this and we will start directly working here. So I prepared here the new section in our ADC.c or the application file, and we start creating this ADC function. We will call it the ADC IRQ on. So let's go here and let's call it a void, because we don't need any output from this. So void ADC IRQ on, and the input, the char, would be only the ADC. So we need to specify which ADC we would like to initiate. Okay, we can get the free code from the ADC function that we created before. So initially, we just need to go and initiate the ADC. That's what we want to do initially. So in this function, we're just targeting the ADC. So we can go back to the function we create before, and this is the pin analog set, this function, and we can copy this code here. So this one is just to get the pointer to the register of the ADC. So now with this ADCX, we will start connecting directly to the ADC, and here we can access to all the registers. And after that, we copy all this code, and we will check it together quickly. So for this one here, so this one means if this ADC has been activated, and this variable we created before, we don't need to activate it again. We don't keep repeating ourselves. And exactly the same. So if our ADC is ADC1 or 2 or 3, and just we go through this. So this is, we are getting a lot of free code. I think we can create it as a function and keep it, but anyway, for kind of education purposes, let's repeat a little bit ourselves. After that, when you run the IRQ function, so let's open here the reference material or the reference manual, and we go to ADC. We need to initiate one activity, and this activity is the continuous reading. So if we go for the ADC registers and we go for CR2 here, what we need to initiate, and this is the bit number 1 in the register, in the control register 2, and this is a continuous activity. What does it mean is when the analog, so here this one, the continuous conversion, so when the ADC or the analog to digital converter get the data, there is a flag here, EOC, end of conversion, is set, and it stops converting until you run it next time. And this is what's happening if we put, if you don't set the speed to 1, that will stop and finish. But what we want is to keep our ADC running and providing this input. So we would like to keep reading the data. So what we are going to do is getting our ADC X and pointing at CR2, putting or equal to. Okay, and on this one is continuous. I hope I'm getting it right. Conversion. Okay, so this is the step 1. And then after that, we need to activate the or enable the IRQ function. So the IRQ function is if you go here and you go here and you put, so you go for the STM32, Control F, and we put ADC like this. There's only one ADC handler. And this ADC handler is the function that will be activated when you do have an interrupt. So this is what you would like to do when the interrupt is happening. Okay, so we can just now understand this why. So this is the handler, so it will be IRQ and a small n or little n at the end. And what we can do if we go here back, what we can write initially, this one NVIC enable, or before that, before the NVIC enable, we need to disable IRQ, disable, I think I messed it up, disable I+2. You have 2 underbar and then disable IRQ like this. That should be like this, disable IRQ. And after that, before disabling, we need, and then we put enable IRQ here again. Instead of disable, this one is enable. And between them, we do have the NVIC, and then here enable IRQ, and we would like to activate the ADC IRQ N like this. And it's already there. So here enable with only one A, and we should be good. Good. That's how you would enable the whole thing, and or enabling or putting on the ADC. So we activate the ADC first, and then we enable the part of the IRQ side. So what we can add, just to finish with that, is adding a variable. We can call it ADC IRQ on the top here. Static ADC, we call it IRQ, and we put it equal to 0. This one, it will be its static char, actually, not just static, like this. And we will be using this one. So if we activated once, because this will happen for whatever, if you have ADC 1, 2, or 3. And if I would like to have an IRQ for ADC 1 and 2, I don't need to reactivate it again. That would be something not really good. So if the other ADC is working, so we can just check if the ADC IRQ is equal to 0, then we can do this like this. So we enable the ADC and we can set our ADC IRQ here to equal to 1. And it's 1 equal that I need. So I hope that the text size is big enough, so I will make the whole thing bigger. so it will be more visible for you guys and ladies. Okay, so we do have our first function here, and let's copy it in the header. So we do have it here in the section. Don't forget, everything is in GitHub, so you just have to follow and be sure that you do have the data, you understand what's going on. And if you still have questions, I'll be more than happy to answer them. So you just put it in the description. Okay, so we initiated the IRQ, the ADC for the IRQ. So only the ADC now is initiated. Then we will assign, we need to create a function. So as I wrote here, so we need to assign a function to, or a pin or a channel to the ADC and let it start. So let's go back here and we go here and we create a new function. So let's make this one smaller so we understand on which one we are focusing. So we initiated. Now we assign a pin. It's like, so let me go to, there's maybe a good picture at the beginning regarding the ADC. Let's check. Yeah, here. So here I'm having the ADC kind of engine, and then you would check about the channels, so which channel you would like to use. And we are going to use here only regular channels. There's someone who asked about injected channels, so if I do have time, I'll be happy to make a video for this. Okay, so let's go here and start assigning the pin or setting the pin for the ADC. So let's go here. So we go for void, and then let's call ADC pin set, pin and set like this. And we need to confirm the char for the ADC, for which ADC, and also which pin we would like to initiate. So here, port pin. Okay. So first of all, the most important thing is to activate the pin and put it on the analog mode. And this is also a code that we already do have. So just copy from here and we can activate it immediately. So by putting this, we are activating the pin and saying to the pin, you are the pin that we will be working with the ADC, or you're ready to work. So we are setting up our pin in ADC mode, so it's ready to connect with the ADC. After that, I still need this function here. Let me take this one, this ADC, and I will need to I will need to get that function. Think somewhere, think for pin the ADC in it here, this one. And I can get my ADC. Let's check, where is it? This one. I can immediately get this one and having this. So this function is a mapper that will take my ADC and I can use it directly. So let's just go back here just to be sure. No, there's also I need to use this function here so I can map it. So I forgot to this is the mapper. So using this ADC, I can use this one. So if I don't use this one, I'm fine. I'm happy I could detect it. So without using this one, I will have trouble for the rest of the configuration. And they will be wondering for a long time what's going on. Okay, good. So we got our ADC, we mapped it. Now we need to map our channel, and we do have exactly the same thing. So if we go the pin analog read, we can get the channel that we would like to set, because as we said before, the ADC is more connected to channels, and those channels are connected to pins. And what we are going to do here is map the channel to the pin. So by inputting the pin and the port, we will get which channel we would like to incorporate with the ADC. Okay, so then now we mapped our channel, we can start doing some serious stuff. So first of all, we can put ADCX here for the control register 1, we put it equal to 0, and I will explain later on what. Then, and we put it for the CR1, because if we go again here to the CR1, CR1 is really the one that manages all the registers and stuff, or the interrupt and stuff, and it's good to initialize it from scratch. If we are using the interrupt, put the whole thing at 0, that will be extremely helpful, so we don't mess up again. So that's one of the things that worked for me a lot. And then, so now we initialize the whole thing, and what we do, actually we can put, yeah, CR1 is good. So we put if channel, so we check if this channel is already not selected, so it's different. If I go different from ADCX, the ADCX of the SQR3, SQR3. So if it's different, then what we can do, we can put the opposite. So this SQR3, oh no, just copy this one and put it equal to the channel. And this just as a reminder, because we reviewed it before, this is where I'm asking my ADC, this ADC regular sequence register. This is where I ask my ADC to read, so which channel. So this is the channel number that I would like to read using my ADC. And as we are reading only the first one, we don't need, just we check on this one. Okay, so we just put the equal. After that, what we need to do is to activate the interrupt. To activate the interrupt, and let's go back in the CR2, and you go to the bit number 10 here. So this is not actually activating the interrupt, but preparing your interrupt for the reads end of conversion selected. This is extremely important, because if you forget to activate this end of conversion, what would happen is that when you get your conversion, it will not stop, and the interrupt will be running again and again, creating a certain infinite loop, and it gets lost within the handler. So you are not able to go back to your main program. So if you don't set this bit to 1, you will get some troubles later on with your program, and you will feel that your microcontroller will be freezing. Okay, so let's put ADCX and then CR2 and I forgot, or equal, and one that is pushed or shifted by 10 steps. Then now we activate the interrupt. So let's go here. Activating the interrupt is CR1 and this one, bit number 5. If you go here and you go interrupt enable for end of conversion. So now the ADC will know that we are in interrupt mode and will be connecting with the handler, and also will know about will be activated the interrupt. So this is really where we activate the interrupt. So in the first function here in the ADC IRQ on, so we're putting on our ADC, and then we later on when we select our pin, we activate the interrupt within the ADC itself. So we go here, ADC X, and we go for CR1 or equal, and that will be 1 shifted by 5 steps or positions. So this one is enabling EOCs, where here is really enabling the interrupt for sure. Finally, we can initiate or start the conversion. So we go here and we put 30, and if we go back, we go to CR2. This is the start conversion of regular channel. So we just initiate the conversion of the regular channel, and that is bit number 30. Start the conversion. Okay, so that's the step where we start the conversion, and here we do have everything well set up. And by this step, we complete how to assign a pin or a channel to the ADC, and we are able to go for the next one, where we will start preparing ourselves with the IRQ handler. So the IRQ handler is quite simple, and I will write it here just to so you don't forget it. And this IRQ handler is valid for all the STM32F4 family, and that's an ADC IRQ handler like this. So this is the function that you will be using to manage the IRQ handler. So let's copy this, and you will be bringing this handle like this here. You will be bringing it here. So what will be happening, and yeah, you need to put a void. So what will be happening is that your IRQ handler is the function that will get out from the main function here and will be reading the data or giving signals. So that's the IRQ handler, and this is a function predefined within the index table as an external interrupt. And you can see here, this covers ADC1, ADC2, and ADC3. Good, so let's also copy, let's go back. Okay, yeah, we need to copy this function too in our header file because we are going to use that. Okay, that should be good and straightforward. Next, after preparing the IRQ handler, we need to check what's going on. So when we get that, we need to check our IRQ signal. And this function will go inside. That will go inside. So I'll put here checking the signal. Okay, so let's go within checking the signal and see what's going on actually inside it. And let's go here and create this function. So let's go here and we can call this function, and this function will return 1 or 0, as simple as this. We call it ADC IRQ, and we add a check like this, ADC IRQ check, and that will input will be only the ADC. So this function will be able just to check if we are having an IRQ in a certain ADC. So we will use here a very simple thing, and that will be the status register. And within the status register, when we will have an end of conversion here, this flag will be set to 1. And this can be cleared by software or also reading the DR register. So clearing here, when you write 1 on it, that will be clearing it. So let's go back here, and we will need only the ADC. So we will need to get this one, and we will put this one here. Let's check if there's an issue. Why? Yeah, I will need a function that we will have to return, but let's create our condition. So if here the ADC X dot like this, oh sorry, for the status register and equal 02 0 a 2 hexadecimal decimal, it's exactly the same thing. So we will do one thing. So we will write the one. So it will be an or equal, and we put like this, and we will return 1. Else, so if we are not reading, if there is nothing to read, we just return 0. Okay, that should remove the warning. And yeah, this reminds me of a good practice, just to go here and always check that this is -0. Good. So now we have our ADC IRQ function. This takes us to the next step, where we are going to start reading the data. And reading the data is not exception from the other one. So just let's copy this here. So we do have all our library ready and good. And close this one so we can read easily. So go back here and reading the data. So here we are going to create the function that will be within the main loop. Okay, so let's go to that and call it. So for this one, the input will be an int, and we will call it ADC RX, just a quite basic one. Input char. What we need is just the ADC. We are going to read the data in the ADC and knowing which predefined channel is connected. So let's get this free function that we get here, and we know our ADC, and we can simply return the data. So we can put int data equal the ADC X and direction here, the direction register, which is the data register, and return it. That's all. Return data. And before returning the data, there's an important step. What we need to do is restarting again, or restarting the conversion again. So we go here, we go for the ADCX CR2, and we put or equal, and we shift 1 by 30 like this. Okay, I think we are good here. Just quickly to check where's the DR register or the data register. It's not direction register, it's just the data register, and this is what where we are going to read the data. Okay, so now we have everything for our code. Just need to copy this and hand it to the header here. And we do have the whole family of functions that will manage our IRQ or the ADC for the interrupt. Now we can do a live test quickly to read the data and confirm that everything is working well. So first of all, let's start the activation. So what we need, so ADC library is already included, so we can start immediately. So let's have an int here. We call it ADC data, and this is the variable or that we are going to track. And in the int main, before going within the while loop, we are going to put ADC IRQ on. And we said at the beginning that one of them, let me check again, which one is connected with which one. So let's quickly review it. I a bit lost the memory on this one. So let's go here and check. What I said is ADC2 will be the IRQ. So ADC2, we will activate the ADC2 IRQ. So let's go here, IRQ on for ADC2. And we are going to set up with the ADC2 PA4. So let's use the function, the ADC, and then pin set function. So we are going to set this for the ADC2. And after that, the pin will be the PA4. Okay, so here we set up our pin, so something is not correct. Declaration of PA4, that's clear. PA4 is declared so here include within the GPIO library that we have created before, gpio.h. So now the pin PA4 is recognized. So here we are good, and we will be start reading the data. So we go here and we put the ADC data will be equal to, and the function we created, which is the ADC RX, like this, the ADC RX, and we will be reading this in the ADC2. Okay. However, each time we will have a handling situation, we need to check. So if we need to check here, ADC IRQ, this ADC IRQ check for the ADC2, then we need to do something. So this is here checking the signal. This is what we are doing inside. And there is something extremely important that we can add to the equation, which is we don't need to read the data if the data is not ready. So what we can do is to add another variable that we call ADC check. Okay, and we put it equal to 0. And here we check if we do have the ADC check. So it means if it is equal to 1, we read the data. Let's push this one here. And also we put set ADC check will be equal to 0. So we put this here and this here. After that, we put here ADC check will be equal to 1. So by doing so, what we do is we initiate our pin, and the ADC will be reading. And each time the data is ready, it will come here and put, okay, the data is ready. We are going to check the which one, the status register. So we will say that we understood that, and we will reset the status register. So this will allow us to get out of the handler. And we say we get this signal and say ADC check, the data is ready. So our program here will just go through here, just read the data and reset our ADC check. Okay, So let's save and build. Okay, so it's a zero error, zero warning. That's quite promising. And let's load the data. Okay, no G-Link connected. I forgot to connect my G-Link. So let me try to find it within the whole mess that I do have for a second. Okay. Yep. And here it is. It was too good to be true. Okay. We should have the signal now and everything is loaded. So let's have a quick check then. And how we are going to do it is by going to the debug mode and go to the ADC data here and send this one to the watch one. So we will be checking if this is reading the data or not. So we go here and we run it. So what's happening here is if I check, yeah, so this is working. This is all good. And let's check if this is also going here. Something is not activating our ADC2. So we do have a kind of an opportunity to check what's going on. So we can, within the debug, start by going through the peripherals. So we go to ADC2 and we check if everything is well. So we do have here, okay, I can immediately see the mistake. It seems that I'm not activating the interrupt, which is really interesting. So let's go here and start correcting this. And I'm activating the interrupt within the IRQ on and something. Let's check. Let's see within the pin setup. This one AX CR1. So this should be enabling the interrupt. So let's recheck again and rerun it. So this is ADC2, but CR1 is not included here. Probably recently I'm making a lot of mistake on. Let's stop it here, reset it, and we go through those one step by step to see what's going on. So if I run here, then run here. So what's going, yeah, I know what's going on. Interesting, really interesting. I forgot to add one extra greater or lower than. So this was kind of a logical code that went through there. It was good. It was a good opportunity for debugging. So let's save, build again, load the code, and go through the debug mode and see what's going on. So if I run now, yeah, I need to stop this and run it again and check what's going on. So something which is good is that this is going through here. So this is good. This is good. So I made a mistake. I should not put the breakpoint. Let's rerun again and see what's happening. Yeah, and we do have now the value is activated and we are able to read. So you could see here that I'm reading the data. So let me bring the video and moving it a little bit. So just bringing back here this video moving. Yeah, I think that's good. So if we said PF4, so I'm now moving this one and hopefully you see it. The value of the data is decreasing and should be reaching 0 now. So we do have the ADC data. Now we are reading the data on the value. So the value is red and there is no issue at all. So now this is good. This is good. So we are getting the value of the data and this is activated and working well. So this step is done And for the next one, what we are going to do is to jump on the adding the other ADC in a normal way. So let's hide this video, adding the other ADC. So we are going to use the function, the normal function we set before. So we would like to have the pin analog set here. So which one we can use, which port, not this one, the pin ADC set. And this one by default is the ADC one. So for the port pin, we are going to use the PA1. So we are going to read the pin AD set in a normal way and also read or check how long it takes to read this one. So what we will do, so we are going to use ADC1 and ADC2. And also we will activate the PA0 and PA5. So pin output set PA0, PA0 as, and also PA5. Okay. And what we will do is here we will put pin right for the PA0, or let's do this for the PA5, and we will want it to turn it on, where after that, just within the cycle to see how long it takes to make all of this, and this one we put it as off. We will do exactly the same thing after this, but for PA0 here. So we have PA0, and after that we will turn it to off. And this is a time analysis. So this one PA0, and in between we are going to use this function to read the data pin analog read, or pin this one directly. We can use this one and read the data for PA0, PA1, sorry. Okay, that should be good. So let's save, build, and let's take this one, let's call it data 1, and we can just have data 2, just for us to read the data, and put PA data 2 will be equal to this one, so become data 1, and PA data 2 will be equal to the value read by the other ADC. So let's save and build, and then we go and load now. All good. So let's debug, and so ADC data does not exist anymore. We can remove it. So we are going to add ADC1 to the watch and also ADC2 to the watch. Okay, and we will show them as a basic decimals, and we can start reading the data here. So we do have now both readings, as you can see. So let me show also the video. So if I move the bar here, or the sliding one, you can see the lower one is reading, changing, and if I move the rotary one, we will have the increase of the rotary data. So we do have both ADC working perfectly well. Good, so now let's hide the video and have the very interesting part where we analyze what's going on. So this is a logic analyzer reading, so which is connected with both signals, and we can start reading and understanding what's going on. So let's read here. Okay, this is good. So, and we can see what's happening between both signals. So this is Yeah, it's quite a long time that is taken here. So you see, this is the PA0, and check. It's huge, takes a lot of time. Something is not correct. Let's check quickly. So this one does not take a lot of time. The PA1, the PA0, if we go here, and this is PA0 connected. So we take a look. PA0 takes 65 microseconds. However, later on the IRQ is taking a huge amount of time. And let's check why quickly. So ADC check will equal to 1. And this one is correct. Let's reconfirm again what's happening. So it seems that it gets here equal to 1. For the PA5, if we got to the PA5, it takes half of a second for the reading. And this is not normal at all. It should be much, much faster than this because the IRQ give a higher advantage. So let's quickly take a look to all our parameters and to be sure that everything is done correctly. So let's go here and check for the ADC1 here and check. So let's get back. Sometimes it's the check itself that is that should need some extra steps. Let's try in the ADC. So this is the reading for the RX. That should be good. But let's try to in the check itself. If we do have this or equal is to 0, so we can put that. That should be clear and straightforward. But why this is not happening as expected, so let's double check again. IRQ1, so this is good. ADC1 is checked, so if the handler, so let's go back, and this is how you debug the IRQ. Usually the IRQ is working, but actually I'm not happy with the result. That should be totally different. That spends a lot of time and it gets messed up. So let's reconfirm this one. So check is here. Let's try something different. And instead of doing this one here, we can read the data directly here. We can read the data here and forget about this one. So we can just keep it and load the data. So what I'm going on, I'm reading directly the data within the IRQ. And let's see what's going on. And this is one of the warning that comes later. So what's going on here? What's happening? You see, this is almost, oh no. Just put this one like this. So the ADC2 is working, but I'm out of the handler now. This is not working anymore. So let's go back again. Okay, we brought it here. Good. So let's check it once again. I'm enabling my AOCs. This is one of the important parts. And then I do have my CR2, which is good. I'm activating again, which works well. But I think the problem, let's add also a check for the ADC one just in case. The ADC one may have generated this issue. And we don't want to check this. Let's get there and load and go for the debug. Okay, I'm reading both now, and if I go to the signal analysis, I still have the same issue. You see, it takes a huge amount of time to work. This is when you don't really program a lot. Let's check it quite furthermore. Let's be radical. Let's be quite radical here. And in the check itself, we put it equal to 0. That's not the best practice ever, but let's be radical there and see if this is improving. It may be the error or the problem of the signal. Let's check now. Let's run it and see how things goes. Yes, that was, and I guess I understood the problem. And you see now we have the right time analysis. And I will keep, apologies, I will keep you the part of this video. So the normal ADC without the interrupt takes 65 microseconds to read the data, where the interrupt is taking a third of that time. So you see how much time saving by having the interrupt in your activity. So that's one of the very interesting part of having an interrupt, and this is what I needed to show you guys. And I'm happy that it worked well, because it's a shame that I got blocked in the code. So it's more the issue was coming from this we needed to put a 0, and this is a problem I get many times, and I always forget because the overrun, because there is a 1 that comes with the overrun and should become a 0, and that keep triggering and triggering and triggering the interrupt. Good. So we had our live test. Then let's finish and go to the before last part, and how to stop the IRQ, or the last function. Just if you use the IRQ and then you'd like to stop it and go back to normal life, let's quickly review how we can stop that. It's quite simple. Let's go here and we put, it's a void, and we call it the IRQ off, ADC IRQ off. And again, what you need as an input is your ADC. And after that, there's a few things to do. So as usual, we will need the ADC like this. And after putting the ADC to off, we need to put, what we need to put is quite direct. So we need to stop. So let's close those one. Let's stop the confusion. We will need this one here. We'll need to disable this. We keep it for later, and the ADC IRQ will be equal to 0 here. So first of all, we need to stop the CR1, so ADC X here, and we need to stop it. So we go to CR2 and or equal, no, actually is and equal, that will be the tilt 1 and this 130. And also for the CR2, we need to stop the continuous reading like this. And so this one is just the 0 BX hexadecimal. Okay, and just here it's not enable but disable IRQ, and we disable the whole IRQ, and that's all. So by doing this function, you do have the IRQ disabled and your ADC can be used in a normal way. Good. So by this one, we completed the whole thing um, through the IRQ. So you should be now really mastering how to use the interrupt system and good to program whatever the STM32 that you do have with a good lesson learned. So let's finish our video for today by a quick warning. So you have seen the issue if you set up in the wrong way your IRQ. That will take much more time that you will need and impact drastically your code. So when you program your IRQ, first of all, careful not to get within this ADC loop that will impact a lot your program. And if you enable your code, imagine you enabled here, you put the ADC on and then you set your pin and you forget to add the handler, your microcontroller will go in a kind of error mode and you will have a hard time debugging your microcontroller. You will not understand. So try not to forget to add the handler when you are using your IRQ. That was all for today. Thank you so much for following this episode. I'm quite happy if you watched this episode to the end, and see you in the next ADC episode where we are going to review how to use the watchdogs. Thank you again and wish you a very good day. Bye bye.